Thank you very much, Angela, and thank you, Monica and Miles, and you, Angela, for the invitation. And hello to everyone. It's a great pleasure to give a talk in the One World PDE seminar. So today I'm going to talk about some joint works with Nicolas Nadirashvili from Marseille, about some symmetry properties for the Euler equations and semilinear elliptic equations. So, okay. So I will talk on the steady Euler equations for an inviscid incompressible fluid, so which can be written this way. So here in my talk, so V denotes the flow, which is not the usual notation for the experts in Euler equations, but I'm using V for the flow, and the flow V is assumed to be divergence free, and we always assume that it is let's say of class C2 in the domain omega. So C2 might seem a bit too strong assumption, but because this equation only involves the first order derivatives, but we will see that this assumption plays a role somewhere in the proof of the results. And the question I'm going to address is the following. So how does the flow inherit the geometry of the domain? We will consider two classes of domains, circular domains. And the question is, okay, in a circular domain, can one find some conditions for the flow to be a circular flow? We will see that this means that the streamlines of the flow are cycles. And we will also consider parallel domains. So parallel domain is like a strip or a half plane or the whole plane. And the question is now, is the flow, can one find conditions for the flow to be a parallel flow? So which means that the flow points into one direction only. And the question is to find some sufficient conditions in dimension 2 to answer these questions. So I will first discuss the case of two-dimensional annuli. So so the notation is the following. So we use omega AB. So omega AB is the open set which is between the two cycles of radius A and B. So I'm always using the Euclidean norm. So the Euclidean norm. Okay, and ER denotes the radial vector, so x over norm of x, and E theta, the perpendicular vector, so the tangential vector. So, okay, so we consider this type of domain, so an annulus. So this is a regular annulus where A and B are given positive real numbers with A less than B. Okay, so the first result is this one. We so consider a solution of the steady Euler equations V, and we assume that V is tangential on the boundary. So which means that V dot ER is equal to 0 on both connected components of the boundary of this annulus. So this condition means that the wall is rigid. So we also assume that the flow has no stagnation point in the closure of the domain. So no stagnation point. Then the conclusion is that V is a circular flow, which means that V is at each point it is parallel to the vector E theta, and from the incompressibility condition, the amplitude of the flow only depends on the norm of x. So v can be written, little v can be written as a function capital V of the norm of x times the vector e theta. And furthermore, the function capital V from the assumption in the theorem, so the function capital V is non-zero. It has a constant sign in the closed interval AB. So this result means, in other words, that the streamlines of the flow, which are parameterized by this family of equations, so xi dot is equal to V of xi. So the streamlines are all concentric cycles. And an equivalent formulation of the theorem is that any non-circular flow, which still satisfies the tangential boundary conditions, must have at least a stagnation point in the closed annulus. And actually, it is in this theorem we can slightly relax the assumption of having no stagnation point in the closed annulus. So in the sense that it is sufficient to assume that the set of stagnation points is properly included into either the inner cycle or the outer cycle. What I mean by properly included is that it is included and not identically equal to. So, okay. So, and even with this assumption, actually, it turns out that the set of stagnation points is then empty. Okay, so this is the first result, and this result can also be viewed as a Liouville type result because it means that the stream function, which I'm going to define soon, so the stream function is radially symmetric. Okay, so this is. Let me first comment this assumption, and let me say that so without this assumption that the flow has no stagnation point, then the conclusion does not hold in general. So it's quite easy. So it was easy to get counterexamples, and a class of counterexamples is given by let's say considering. So one can first consider this family of semilinear elliptic equations in the domain omega AB. So if you consider any classical solution U of this equation for a function f which is let's say of class C1 or Lipschitz continuous, and assume that U is a constant on both connected components of the boundary of the domain, but it may take different constants. Then if you if I define V to be the orthogonal gradient of U, then V is automatically divergence free, and it also obeys the Euler equations with a pressure P which is given explicitly in terms of U. So therefore, if we consider, and this is true for any such a solution U of this type of equation. So therefore, if U has a critical points, then this means that V has a stagnation points because the critical points of U are the stagnation points of V. And furthermore, if V is not radially symmetric, then V is not a circular flow. So, for instance, if we consider this principal eigenvalue problem, so this is a problem in 1D, so in the interval AB. So we consider this operator, and so the first two terms of this operator stands for the Laplace of a radially symmetric function, and then we have an additional term here which is r minus 2 times phi. So this operator has a principal eigenfunction and principal eigenvalue. So let me denote lambda the principal eigenvalue and phi the principal eigenfunction with Dirichlet boundary condition. So the principal eigenfunction is characterized by the fact that it has a constant sign in the open interval AB. So now now if I define u to be phi of r times cosine theta in the usual polar coordinates, then by definition of the function phi, the function u solves this equation, so which is a particular linear and therefore particular semilinear elliptic equation, and this function u has 6 critical points in the closed domain, 2 on the inner boundary, 2 on the outer boundary, and 2 in the open annulus. And therefore the flow v is a non-circular flow because the function u depends on theta, and the function v has 6 stagnation points. So therefore it's quite easy to construct examples of flows having stagnation points and which are not circular. Okay, but I also would like to point out that the condition that the norm of v is strictly positive in the closed domain is obviously not equivalent to being a circular flow, because there are circular flows with stagnation points besides the trivial flow. So for instance, if I consider this operator now, so which stands for the Laplace operator in radial coordinates, so for radially symmetric function, without the additional r minus 2 term. So if I consider phi to be the principal eigenfunction and mu the principal eigenvalue, still with Dirichlet boundary conditions, then the function u, which is u of x equals to phi of norm of x, solves this linear equation, Laplace u plus mu of mu times u is equal to 0, and the set of critical points is equal to the whole to some cycle with a radius r star, which is between a and b. And the flow v, since u is radially symmetric, then v, which is the orthogonal gradient of u, is a circular flow with infinitely many stagnation points, because the set of stagnation points is the whole cycle of radius r star. Okay, so I would like to spend some time to show you the main ingredients of the proof. Here, the proof of this result in this regular annulus is quite easy to understand. So I'm going to present it to present the main steps. It's quite easy to do that. So we consider a flow V satisfying the assumptions of the theorem. So it satisfies the rigid wall boundary conditions, and it has no stagnation points, say in the closed annulus. So since the flow is divergence free, and since the normal component is equal to 0 on the inner boundary, the flow V has a stream function u. So there is a function u, whose orthogonal gradient is equal to v. So the orthogonal gradient is of u is du over dx2 and minus du over dx1. Okay, and this function u is unique up to additive constants. And so therefore we can, and furthermore, since v is tangential on the connected components of the boundary, the function u is constant on both connected components of the boundary. So therefore, without loss of generality, I can assume that u is equal to 0 on the outer boundary, and u is equal to some constant c on the inner boundary. So I don't know what c is, but there is such a constant c. So now in this picture, I claim that any streamline of the flow, so the streamline are the trajectories parameter, so trajectories given by the flow. So any streamline gamma intersects any trajectory capital sigma the gradient of the stream function. So there are several facts. So first of all, so along any streamline gamma, the stream function is obviously constant. And since the flow has no stagnation point, the stream function u has no critical point. And therefore any streamline gamma has to surround the origin. So gamma surrounds the origin O. So by that I mean that so gamma is a closed curve, and the connected components it is a Jordan closed curve, and the bounded connected components of the plane minus gamma contains the origin. So we have this type of picture for gamma. And now let me consider any trajectory sigma. So let me consider a trajectory sigma starting. So sigma is so a curve parameterized by this type of equation. So sigma dot of t is equal to gradient u of sigma of t. So let me start with at a point which is on the outer boundary. So this since the gradient of u is orthogonal to v, so the gradient of u is therefore orthogonal to the boundary. So this is like the gradient of u at this point. So I should maybe okay. So the gradient of u is like that. So up to changing v into minus v and u into minus u, I can always assume that the gradient of u here points inwards. So now if I consider this equation, so this equation is defined at least in a right neighborhood of 0. So if I say that, so let me call a this point. If I say that sigma of 0 is equal to a, so this function sigma is therefore defined in a right interval of 0. And the trajectory capital sigma cannot come back to the outer boundary because along sigma the function u is strictly monotone. So it's an important fact. So the function u is strictly monotone along sigma, and since u is constant on the outer boundary, so the curve capital sigma cannot go back to the outer boundary. And also it cannot make infinitely many terms because u is bounded in the closed annulus. So therefore this capital sigma has to end at the inner boundary, somewhere at the inner boundary. And therefore we have by continuity any streamline capital gamma has to cross capital sigma. So we have this picture. So there is a crossing between these two curves. So let me erase some things. So necessarily we have this picture. So so we have a crossing point, and which is unique because little u is strictly monotone along capital sigma. Okay. So this is so we have this picture, and what we want to show is that u is radially symmetric. And in other words, so we have to show that what we want to show is that any streamline capital gamma is a cycle. So far we know that it surrounds the origin. Okay, so now how do we progress? So with that, so even if it means changing u into minus u, since the function u was strictly monotone along the curve capital sigma, we can assume without loss of generality that c is strictly positive. So c is the value. So we have u equals to c on the inner boundary and u equal to 0 on the outer boundary. So without loss of generality, c is positive. So c is non-zero and assume c is positive without loss of generality. And okay, so now since any streamline of u intersects capital sigma, so we had capital sigma here, we consider one capital sigma, and so this was capital gamma. So since little u is increasing, now it is increasing along sigma from this point to this point, and therefore any streamline which is in the open annulus, so on any streamline which is in the open annulus, the value of u along gamma is equal to the value of u here, which is strictly between between 0 and c. So therefore, since any streamline intersects capital sigma, we get that u ranges between 0 and c in the open annulus. So everywhere u is between 0, u of x is between 0 and c for any x in the open annulus. Okay, so now we consider the vorticity of the flow. So the curl of the flow, which is a scalar function here in dimension 2. So which is the Laplace of the stream function. So this vorticity is constant along the streamlines. And this is only where we use the only place where we use the Euler equations, as a matter of fact. So this is a well-known fact. And okay, in the classical literature on the Euler equations, so the vorticity is called omega, and the stream function is called psi. So let me call it u because I come from the elliptic equations, and u would satisfy an elliptic equation at the end. And okay. So so the vorticity is constant along the streamline. So therefore, both the stream function and the vorticity are constant along the streamlines. And therefore, we get an equation. We can write an equation between the vorticity and the stream function. So an equation which is a semilinear elliptic equation of this type in the whole domain, in the whole annulus. So why is that possible? Because it is sufficient to define the function f. It is sufficient to satisfy to have this equation along the trajectory capital sigma. So we have this equation along capital sigma. Once we have it along capital sigma, then we have it everywhere because each streamline intersects a capital sigma. So now to have this equation along capital sigma, so we can just define the function f like that. So in such a way that this equation is satisfied along capital sigma. And here, so we have theta, which is defined like that. So in other words, we have Laplace u of sigma of t plus f of u of sigma of t, which is 0. And we have the equation along capital sigma, and then we have it everywhere. So of course, let me point out that it is quite classical to have such an equation, and in the literature on the Euler equations, the function f is usually called the vorticity function and usually called the gamma. So let me call it f here. So it's quite classical to have this equation locally around any point which is not a stagnation point. So the main interest of this proof is to have this equation, is to derive this equation in the whole domain. Okay, so once we have this equation, we can use a theorem of Boyan-Sirakoff. So which, yes, I forgot to mention that the function f, which is defined here, the function f is actually of class C1 in its range, in the range of u, because the function remember that the function, the flow V was assumed to be of class C2, and therefore the vorticity is actually of class C1. So U is of class C3, vorticity of class C1, and therefore the function f by the chain rule is of class C1. And this plays a role. So in the theorem of Boyan-Sirachov, so assume that we get a function f which is Lipschitz continuous. So it would be sufficient to have Lipschitz continuous in the previous slide. So we can slightly relax the assumption on V like C11, but not too much more to apply this theorem. Okay, so assume that f is Lipschitz continuous and consider any set omega AB, so which is now any domain between two concentric spheres, and this result holds in any dimension n. So here n is any integer larger than 2 or equal to 2. And consider a classical solution U of this equation in this omega AB, and such that U is equal to 0 on the outer sphere, and U is equal to some constant C on the inner sphere, and assume that U is between 0 and C in the open set omega AB. Then U is radially symmetric, and furthermore decreasing with respect to the norm of X. Okay, so this, so for those who know the classical results of Guidasny-Nirenberg, so this theorem looks like the classical result of Guidasny-Nirenberg, let's say in a ball for positive solutions of such an equation, which are equal to 0 on the boundary of the ball. So here we consider a domain which is between two spheres, and to get the result, we need to consider two different values on the inner and outer spheres. Otherwise, the method of Guidasny-Nirenberg, based on the moving plane method of Alexandrov and Serin, would only get a partial results, partial monotony in let's say in any direction, but for radius larger than half of the radius. So here to get because there are two different conditions on the inner and outer spheres, we get the whole symmetry. So this is a theorem of Boyan-Sirachov. So the function U is radially symmetric. And so here so for our problem for the Euler equation, so we can just apply this theorem in dimension 2, and we get that U is radially symmetric, and therefore the flow V, which is the orthogonal gradient of U, is a circular flow. And the proof is done. Okay, so this is the proof in a regular annulus. So now I would like just to mention briefly some other results so first of all, in exterior domains. So by that I mean the complement of a disk of radius A. So somehow, so there is no outer boundary, and the boundary has only one connected component, which is a cycle of radius A for some A positive. So we assume that the flow V is still tangential on the boundary, so on this cycle CA, and we assume further conditions. So we assume that this first condition, that the flow has no stagnation point in a strong sense. So the infimum of the norm of V is strictly positive. And we also assume some condition at infinity, so which says that the radial component of the flow is small at infinity. So more precisely, namely little o of 1 over norm of X at infinity. And the conclusion is still the same. So the flow is a circular flow. And so it can be written, so little v can be written as capital V of norm of X times the vector E theta of X. And capital V is non-zero. So so this means that the streamlines are all concentric cycles. And this means also that the stream function u, which can still be defined, is radially symmetric. So it's a Liouville type result for the stream function. And also I would like to mention that the flow here is not assumed to be bounded from above. And okay, we can, so for instance, there are obviously circular flows which are not bounded from above in norm. Okay, so we have the same conclusion with similar assumption in the domain and further conditions at infinity. So I would like to comment on this condition at infinity. And I would like to say that without this condition at infinity, the conclusion does not hold in general. By that, let me just show you one counterexample. So I consider a function u which is defined by this formula in polar coordinates. So this example is cooked up in such a way that the Laplace of u is just a constant, which is 8 over a squared. And this function u is a constant on the cycle of radius a. So since we have this type of semilinear, which is actually linear here, equation for u, so the flow v, which is the orthogonal gradient of u, is a solution of the Euler equations with some pressure which can be explicitly computed. And the flow v is, so it's given by this formula. And so the flow v satisfies the strong assumption that it has no stagnation point in the domain nor at infinity. The infimum of the norm of E is strictly positive. And this flow v, but this flow v does not satisfy the condition at infinity. So the radial vector, the radial component of v, which can be, it is big O of 1, but not little o of 1 over norm of x, as the norm of x goes to infinity. So this flow v does not satisfy one of the conditions of the theorem, and the conclusion does not hold. So the flow v is obviously not a circular flow. And here in this example, the streamlines, in this example, the streamlines of the flow, which are the label sets of u, are still surrounding the origin, but the limiting radial oscillation of the far streamlines is a over 2. By that I mean that if we consider a far streamline, and that would be the smallest radius, and that would be the largest radius. So the oscillation of the radius is converges to a over 2. So these streamlines do not converge to cycles at infinity. Okay. But we do not know in this. So here we do not know whether this condition at infinity for the radial component of the flow, we do not know whether this condition is optimal. So this counterexample means that if the radial component is a big O of 1, in general, the conclusion does not hold. But there are some other ranges between little o of 1 over norm of x and big O of 1. So we do not know the optimality of this condition. But in the proof, it is strongly used. But okay. And the scheme of the proof is so shares some common features with the previous one. So we can still define a stream function u. And without loss of generality, we can assume that it is equal to 0 on the cycle of radius a, so the boundary of the domain. And without loss of generality, we can also assume that the radial component of the gradient of u on CA is strictly positive. Okay. So remember that the flow has no stagnation point in the whole domain, in the closure of the domain. So the gradient of u doesn't vanish anywhere. Okay. And okay, so now we consider also a trajectory of the gradient flow, so parameterized by this equation, starting from one point of the inner cycle. So I consider any A, so that would be CA, so the boundary, and I consider any point A on the boundary, and then I consider the trajectory, capital sigma, of the gradient of U. So this so the trajectory sigma, if it is, so at any point of sigma, the streamline containing this point intersects capital sigma orthogonally by definition. And along the capital sigma, the function mu is strictly monotone. And also we can show that this capital sigma, this curve capital sigma, goes to infinity. And furthermore, the value of u along this curve capital sigma also goes to infinity. Here T max denotes the maximal, so the right hand side, the right bound of the maximal interval of definition of little sigma. So, and also now I claim that for each point, somehow, for each point on capital sigma, the streamline containing this point surrounds the origin. So this is streamline capital gamma. So this streamline surrounds the origin. And this proof is done by continuation argument. So this is true obviously when the point is here, when we take the point A, because by definition the cycle CA is a streamline, so therefore it surrounds the origin. And this is true for any point along capital sigma. And this is where we use the assumption that that the flow has no stagnation point in this strong sense. And therefore it follows that all streamlines surround the origin, because now if you consider any streamline, so any streamline along any point, then since when the points along sigma are very far, then the streamlines have also to be very far, because U converges to infinity along capital sigma. And therefore any far streamline has to surround this other streamline gamma x here. If you consider any point x here fixed, then then the green streamlines surround the streamline gamma x, and therefore gamma x has to also to surround the origin. And therefore, it follows that U is strictly positive in the whole domain, because little u is strictly increasing along capital sigma, and therefore along capital sigma U is actually positive. U is positive, so therefore U is positive everywhere, because each streamline intersects capital sigma. And we can also show that the radial oscillation of the far streamlines goes to zero. So the radial oscillation, which is defined like that. So the maximum of the norm of y when y belongs to Cx minus the minimum goes to zero when norm of x goes to infinity. So in other words, the far streamlines look like cycles. And also we get, so as before, we get an equation, a semilinear elliptic equation for the stream function in the domain for some C1 function f. And we can now adapt the method of moving planes of Alexandrov, Serin, and Gidasny-Nirenberg to get the monotonicity of U in any direction E up to some epsilon. So this is a quite difficult point, technical point here. So we cannot apply the same result of Sirachov as before, because we do not know that the streamlines are cycles. This is what we want to show, but we know that the far streamlines look like cycles because of this condition, but they're not exactly cycles a priori. But somehow, if we can apply we can still apply the method of moving planes by comparing the function u to its reflection with respect to some moving planes and to some hyperplanes, and then we move the position of the hyperplanes in any given direction E, and we get the conclusion. But when we do that, we get the conclusion up to some epsilon, and then we pass through the limit when epsilon goes to 0. So it's quite complicated. This is quite a technical part, and with a limiting argument, we get at the end we get the radial symmetry of U, and therefore we get that the flow V is a circular flow. So here, this is the most technical point here, and we also use the fact that the radial component of the flow is little o of norm of 1 over norm of x at infinity to get the conclusion. Okay, so I had to skip the details, and I would like now to, okay, I don't have time to present further results, but there are also further results in punctured disk when we subtract the origin, and also in the punctured plane, so R2, and we subtract the origin. So we get such results also in this configuration, but I don't have time to talk about that. I would like to mention, let's say, one serine type free boundary problem. So it's the following. So now we consider a domain omega, but we don't know what omega is a priori, but it is, we assume that it is a C2 non-empty, simply connected bounded domain of the plane. And we assume that we have a flow V, which is, let's say, of class C2 in the closure of omega, and which is tangential on the boundary and also constant on the boundary. So the norm of V is constant on the boundary. And we also assume that V has a unique stagnation point in omega bar, which is therefore an interior point. Then up to shift, the domain is the disk of radius r centered at the origin up to shift, and the unique stagnation point of V is the center of the disk, which is the origin up to shift. Okay, and furthermore, V is a circular flow. So this is a serine type result because somehow we have, because the domain is not given, but we have overdetermined boundary condition for the stream function. So the stream function U is both constant on the boundaries of omega, and also it has a constant normal derivative on the boundary. So this is like the classical serine problem for the equation Laplace U is equal to 1 or equal to f of U in such a domain with overdetermined boundary conditions. And the proof uses the moving plane method, which was used by Serine in this configuration, up to, let's see, but we have to do that, but we since the function f, which appears here, may not be Lipschitz continuous at the critical point of view. So we cannot exactly apply the result of Serine, but we do that by subtracting some small neighborhoods of the unique critical point of view of size epsilon, and then we pass through the limit when epsilon goes to 0 in the Serine arguments. So so this is where we get this result, and okay, there are also related results for other type of conditions, let's say assumptions on the flow. I think I don't have time to present that. I would like to mention the last result, let's say in the whole plane R2. Now, sorry, the whole plane R2. So we still consider the Euler equation but now in the plane R2. So there is no boundary now, and we assume that the flow V satisfies this condition. So first of all, it has no stagnation point in this strong sense. So the infimum of the norm of V is strictly positive. And we also assume that the flow V is bounded. Then the conclusion is that the flow is a parallel flow, which means that there is a unit vector E and a function capital V of one variable, such that the flow little v can be written as the function capital V of x dot perpendicular, the orthogonal vector of E times E. So the flow V is parallel to the vector E. So the streamlines of the flow are parallel to the vector E. But we don't know what E is a priori, so because there is no boundary, and E can be anything a priori because you can rotate a parallel flow to get another parallel flow. And okay, so but there is such a unit vector E. So so in the domain R2, so with this condition, the flow have to be parallel flows. So as a consequence, if we have periodic flow, if we have a flow which is periodic, if we have a flow which is periodic, if the flow is if the flow has no stagnation point, then it is a parallel flow. Okay, and this condition is also stable with respect to the n infinity norm. Okay, and in the proof, we use the stream function. We can still define the stream function u, and okay, let's go to the last slide. I think we can define the stream function u, and we can show that the streamlines are all unbounded, and that the trajectories of the gradient flow are also all unbounded. And we can also show that the level set, each level set of the stream function has only one connected component. So somehow there is a foliation of the plane by the level sets of u in a monotone way. And therefore, from these facts, we can write an equation for the stream function u. So there is a function f such that the function u satisfies this equation globally in the whole plane and not only locally. And once we have this equation, but now the problem is that we cannot apply a continuation argument as before because there is no obvious streamline. The flow is defined in the whole plane R2. There is no boundary, so no obvious streamline as before. And but since we have a semilinear elliptic equation for the stream function u, so the all first order derivative of u satisfy the same linear equation, and therefore the argument phi of v, which can define continuously in a unique way up to multiples of 2 pi. So the function phi, so the argument of the flow, satisfies a linear equation which is uniformly elliptic because the flow v is between two positive constants. And now there is a key estimate, so we can show, which is quite difficult actually, we can show that this argument phi does not grow too fast at infinity. So more precisely, it grows at most like big O of the log of a norm of x at infinity. So somehow the streamlines and so do not make so many turns at infinity. And since we have this uniformly elliptic for the function phi, we can use a famous result of Moser based on the Harnack inequality. that if phi were not constant, then phi would grow at least, so the oscillations of phi in large cycles would grow at least algebraically with respect to the radius. So therefore, since this function phi grows at most logarithmically, it has to be constant. And therefore, V is a parallel flow. Since the function phi is constant, V is a parallel flow automatically. And the proof is done. So I think I'm going to, so this is I'm going to stop here. And thank you for your attention.